figure out what the magnitude of vector h is? Well, we need to know the distance. If you think about it, magnitude is distance. We gotta know the distance from here to there. I can make a triangle out of this thing. And then, well, that was right 1, 2, 3, 4, and I'm 2. And if I want the distance, I gotta use the Pythagorean theorem. So I'm gonna go 4 squared, that's 2 squared, equals I don't know squared, so let's just call it 8 squared for now. And then 4 squared is 16, plus 4 equals 8 squared, that's gonna be 20, 8 squared. Take the square roots, I wanna get rid of the squared. When I think about the square root of 20, I don't like 2 and 10. I do like 4 and 5. Because I know the square root of 4 is 2, root 5 is what I wanted. So what is the length or the magnitude of vector h? It's 2 root 5. So we're at the point where I think you're already ready for a U try. So let's give this one a shot. Number 1, I want you to calculate the magnitude of k. Number 2, I want you to calculate the magnitude of 3k. So think about it. Draw 3k real quick. Make your triangle. Same idea down here. I want to know the magnitude of negative k. So remember, that doesn't change, does not change magnitude, does change distance. It gets in the way. Let's go ahead and check your answers. The magnitude of vector k should have been 5. It's a nice Pythagorean triple. 3, 4, 5 triangle. Magnitude of 3k should have been 15. It should have drawn it out going right 9 up 12. It's redo k 3 times. And then number 3. Well, negative k is, well, instead of going right and up, it's going to go left and down. But if you look, it made the same darn triangle. So duh, it's going to have the same answer. Now, I want to really quickly look at the 15. I could get 15 by going, well, 3 times 5. Well, if we look at it, 3, 3k, 5 is the magnitude of k. So that's another way I could do this. So let's go ahead and write down some properties of magnitude. The first one. Well, magnitude always has to be positive. Well, it's a length. We can't go negative distances. You've never walked negative 6 feet. Doesn't exist. Second property is what we were talking about here. If you have a scalar multiplier, that's what b is going to be in this case, times a vector v, where that's a scalar, then this equals whatever b is times the magnitude of v. And that's what happened right there. We had the 3 was our scalar, and we knew that the magnitude of k was already 5. 3 times 5 can give us the 15. And then our third property is, well, connecting the first thing and the third thing. Vector v is the same, the magnitude of vector v, sorry, is the same as the magnitude of negative v. Which makes sense, because remember how we defined it yesterday, and I hinted at this a second ago. The negative doesn't change magnitude, changes direction. So yeah, they should be the same. Those are the 3 properties of magnitude. Second big topic we're going to talk about today is called position vectors. Well, position vectors is just a vector whose initial point is on the origin. And it will be denoted one of 2 ways. It'll give you the vector name for v equals, and then for us, it'll be c, comma d. Notice these are not parentheses, because they're not. And then, this also has a second name. Sometimes this is called the algebraic vector. Algebraic, there we go. Algebraic vector. Never going to use that name again. Or it might be denoted in what's called ij form, with ci plus dj. Now c is going to be the horizontal component, just like your x. D is going to be the vertical component, just like your y. So we need to write a position vector for the vector below. Well, it says it's a vector whose initial point is on the origin. So let's go to the origin. Draw a graph. Put the initial point on the origin. And then follow what this guy does. He went right 1, 2, 3, 4, 5. Down 1, 2. Well, let's count again. 1, 2, 3. So 1, 2, 3, 4, 5. 1, 2, 3. And that is visually what a position vector positive 5. So we can say W equals 5. And I'll go ahead and show you the second way too. W equals 5I. And then we got to look at the vertical component. Now, direction absolutely matters. That went down 3. So that's a negative 3. So we can say negative 3 or minus 3j. That's how you write a position vector for W in this picture. Now, position vectors are the vector whose initial point is on the origin. Now, the reason why it's so important that we talk about these is because, look, I just translated that vector to the origin. Now, I didn't say anything specific about this vector, so we can honestly do this with any vector. And that's why it's so important that we did this. It's because now we have a unique way to represent all of these different types of vectors. Let's take a look at example 2. We want to know, what's the position vector between 5, 6 and negative 2, 1? Now, we're going to want to make sure we get our vector and then move it to the origin. So, let's get a vector. So let's graph. Where is 5, 6 and where is negative 2, 1? So, here we go. 5, 6. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Notice I'm starting there because it says I have to and then end over here. The order absolutely matters because it's a directed line segment. And then negative 2, 1. Negative 1, 2, 1. So going from here down to there. So this one went down 1, 2, 3, 4, 5. And went 1, 2, 3, 4, 5, 6, 7. So if I start at the origin, down, what was it again? 1, 2, 3, 4, 5. So down 1, 2, 3, 4, 5. And then left 7. 1, 2, 3, 4, 5, 6, 7. Going down to here. Now, I'm noticing a lot, well, I'm not noticing because I'm not here. But knowing you guys, a lot of you probably have caught on to the shortcut by now. Fine, use it. I don't mind. Draw our triangle real quick. And if we look at our position vector, well, we went down 1, 2, 3, 4, 5. So negative 5. And that's the vertical component. And we went left 1, 2, 3, 4, 5, 6, 7. And that's the horizontal component. So let's write it all together. Didn't name it anything, so don't worry about it. We went horizontal component was negative 7. Vertical component was negative 5. And then we could write it in ij form also. So we could write it as negative 7i, because remember, I is the horizontal component, minus 5j, because 5 negative was the vertical component. All right, here's what you try. So for number 1, write a position vector for that vector below. Let me go ahead and name it. It's going to be vector W. And then what is the position vector between those 2 points? And what is the position vector between? You know what? Just to mess with you, it's not possible. So go ahead and check your answers, please. Now, a couple things I wanted to clarify. First thing, we're not always going to be writing both position vectors. Usually, they'll give you one or the other, not both. Second thing, we'll notice that all of them came out negative plus. That does not happen everywhere. I don't want you getting the habit of that happening. The reason that happens is if you look at all of ours, all of our horizontal components were negative, and all of our vertical components were positive. So that's why I make negative instead of positive. If instead our horizontal component was positive, but our vertical component was negative, then that would have been positive and that would have been negative. Alright, so example 3. We want to graph the position vector of 3, negative 8. Well, remember, 3 is going to be the horizontal component, and negative 8 is going to be the vertical component. But there's one other catch. It's a position vector. So it needs to start at the origin. So, on the origin. We're starting there. And then it says it needs a horizontal component of 3. Well, that's positive, so go right, 1, 2, 3. And it says it needs a vertical component of negative 8. So down 1, 2, 3, 4, 5, 6, 7, origin. But we got to notice that our horizontal component now is a -2. And our vertical component now is a -5. So we want to go horizontally in the -2. So -1, -2. And vertically -5. So -1, 2, 3, 4, 5. And we are done. Alright, here's the new try. So to get going, I want you to graph on number 1 and number 2, 3 and 4. Remember, that means magnitude. And I want to know the magnitude of 8W after that. And now for 6 and 7, take it in 2 steps. Step 6, graph V plus W. And then step 7, what is the magnitude of V plus W? Alright, go ahead and check your answers, please. That's work for later. That's work for later. Your vectors should be the same. And then what's the magnitude of V? Well, I do the triangle, Pythagorean theorem. Should we get the square root of 41? Same idea with, what is it? Magnitude of W. Pythagorean theorem. You get 10. Now, what's the magnitude of 8W? Well, it's going to be 8 times the magnitude of W. Well, W was 10, so 8 times 10, 80. Should still remember this from yesterday. And then from there, well, how to draw the triangle? Well, remember, we're going from the start to the end. So then drawing that triangle. And you could have gone down 1 and left 12. Fine with me. Either way, it'll come on the square root of 145. So if you look at yesterday's notes, we have an idea of equal. We talked about how vectors have to have the same magnitude and the same direction. Well, now that we've discussed position vectors, we can come up with a new idea of equal. Because if we think about it, these position vectors will help us determine if these are equal. If V equals C comma D, then W is equal to F comma G. So C and F are both the horizontal components, and D and G are both the vertical components. Vector V is equal to vector W if and only if C is equal to F, meaning that the vertical, or no, that's horizontal. The horizontal components are equal and needs to be both. The vertical components are also equal. That is, D is equal to G. Now the reason why that works, think about it for a second. They're going to be going in the same direction because, well, they're the same type of coordinate. So if this one's going right and up, well, this guy's the same thing. He's going to be going right and up also. Now, why are they going to have the same magnitude? Think about the Pythagorean theorem for a second. When you did your Pythagorean theorems, the shortcut was really you're doing this guy squared plus that guy squared equals something squared. And you were calculating that distance, and that gave you your magnitude. Well, if C is equal to F and D is equal to G, then whenever you do the Pythagorean theorem, whatever number that comes up to, we're going to have to be equal, because these were equal. So our new idea of equal is now that if the components are equal, then the vectors are equal. And this is the beginning of something called component-wise thinking. And tomorrow we're going to talk way more about components.